All right, welcome to phase changes and phase change diagrams. This is covering pages 34 through 37 in your notebook. Okay, so today we are going to be learning about phase changes. Phase changes are something you're relatively familiar with because you're familiar with phases, or what you may have heard of before as states of matter. Things like solid, liquid, and gas. And so we're still going to be talking about solid, liquid, and gas, but we're going to start out with talking about what those things are, and then how do we get changes that occur between them. So look, starting on page 35, we're going to look at phase changes. So the first thing we have to do is we have to say, well, what determines a phase change? And the thing that determines a phase change, or a phase itself, is how the particles are arranged. So when we're talking about phases, we're talking about things like solid, liquid, and gas. And solids are different from liquids. Liquids are different from gases. And we can tell that based on how their particles are arranged. So if we use our fists, we can think that a solid is vibrating in place. But those particles are kind of locked in their location. They're just moving in place. Once we move to a liquid, those particles are able to slide past one another. And so we get that fluid movement. And then lastly, when we get to a gas, those particles separate from each other and bounce all over the container. But it's the particle arrangement and how those particles are packed together and how they're moving that determines what phase we are in. Well, particle arrangement is determined by two things. That's both temperature and pressure. Temperature is the average speed or kinetic energy of particles, and so the faster particles are moving, the more likely they are going to be able to break those attractions between particles and move around. Pressure also has an impact because pressure is going to either force those particles together or allow them to spread out. And so if we look at our pictures here, we've got solid, liquid, and gas, and we can see that in solid, those particles are tightly packed. In liquid, they're still tightly packed, but they are able to move freely around one another. And lastly, we have gas, which is able to move freely throughout the container. And so if we can kind of define those, in that because of that particle arrangement, solids have a defined shape and volume because the particles are locked in place. Although they are moving, they're going to have a set shape and a set volume. Liquids change slightly because although they are still packed together pretty closely, they are able to take the shape of their container because they're able to slide past one another. And so solids are different from liquids in that solids have a defined shape because the particles are locked in a position. Liquid, we can change the shape because they're able to slide past one another. And then lastly, we have gas. Gases are going to take the shape and volume of the container because they don't have very strong particle attractions, and so they're able to move all over the container. When we take into account the idea of pressure, solids are going to be more dense because they are pushed together, and gases will be less dense because they're able to spread out. And so then we can start talking about phase changes. And so we're going to switch over to page 34, and we're going to look at phase changes. So when we talk on page 34, we're going to kind of describe what each of these phase changes are, and then we are going to learn about some terms called endothermic and exothermic. So if we think about melting, melting is the change from solid to liquid, and that is going to be what we call an endothermic phase change. So endothermic refers to the idea that heat or energy was required in order to make that change. And if you think about the fact that the particles are kind of locked in place and vibrating to freely sliding past one another, that would require an increase in energy. So that's an endothermic change. Melting's reciprocal partner is freezing. Freezing is going to be the change from liquid to solid. And so those particles have to slow down and have more particle attraction to kind of be locked in place. And so they're going to have to lose energy. So we consider that an exothermic change. If we continue on, our next pair of reciprocal phase changes are evaporating and condensation. Evaporation is a liquid going to a gas, and that's going to require an increase in energy. Condensation is a gas going to a liquid, and so that's going to require a release of energy. And then our last two are two that you may not be as familiar with, sublimation and deposition. This is kind of what dry ice does, and the reason why we call it dry ice is it goes from a solid to a gas without a wet phase, but those particles are going to be moving faster, so that's an endothermic change. Deposition is the reverse of that, so the deposition is going to be the change from a gas back down to a solid, and that is going to be an exothermic phase because those particles have to slow down. As we can continue on to page 34, we're just going to further clarify that. So in our Venn diagram, we've got endothermic and exothermic. And so what I want in this endothermic section is I want you to tell me the phase changes. There are 3 endothermic phase changes. so I want to know those. I also want to know what does it mean to be endothermic, and you'll have a better idea of that in just a moment. And then I want a picture of the graph. We're going to see the graph on the bottom of page 35 when we're graphing endothermic phase changes, and so you put the graph there. And then you would do the same thing for exothermic. I want to see those 3 phase changes. I want to see the definition of what an exothermic change is, and then I want to see an example of an exothermic graph. In our phase change triangle, what we're going to do is we're going to take the 6 phase changes that we talked about at the top, and we're going to put them into our triangle. So we're going to start by just labeling. I can tell that this is solid, this is liquid, and this is gas based on the particle arrangement. And then I ask myself, in order for a solid to become a liquid, it must melt. In order for a liquid to become a solid, it must freeze. So those are the names of my phase changes. And then I'm going to grab a highlighter. And for every phase change that is going to be an exothermic phase change, one that's going to require a release of energy, I'm going to highlight those exothermic phase changes one color, and then I'm going to highlight endothermic phase changes that required a gain of energy the other color. So now let's shift over to page 35, and we're going to look at really defining that endothermic and exothermic. So an endothermic phase change is anything that gets hotter or gains kinetic energy through the process, because endothermic means to gain heat or to take in heat. So an endothermic change is going to absorb energy or take in energy from the surrounding area, and that's going to increase the randomness of particle collisions. Because those particles have more kinetic energy and they're able to move faster, they're going to collide with the particles around them more often. An exothermic phase change, on the other hand, is going to be losing heat energy. And so they're going to release energy to the surrounding areas, which means that those particles are going to move in a less random way, and so we're going to decrease the randomness of particle collisions. And really, this is going to be described when we look at our phase change diagrams. Our phase change diagrams show us what happens as we heat or cool a substance through its phase changes. In order to do that, the first and most important thing we need to know is kind of our key sentence about phase changes. During a phase change, temperature remains the same. So during a phase change, temperature remains the same. Whenever we look at a phase change diagram and we're looking at what happens to temperature and energy over the time, whenever the temperature remains stable, like what we see happening here and here on the diagram, that's going to be a phase change, because during a phase change, the temperature remains the same. Now, heat energy is still being absorbed or released, but that absorbing or releasing of energy is changing particle arrangement, so it's either making or breaking those associations between particles. But the actual temperature or average kinetic energy of the substance is going to remain the same throughout the phase change. So this is true of any time you have something that was completely solid becoming liquid. When it is completely solid and there is no liquid, you're able to heat or cool it. But as soon as some of that solid starts to melt and you get 2 phases, both solid and liquid in the container, that temperature will remain stable throughout the entire melting process until it's all liquid. Once it's all liquid, it can heat up again, and then we can heat it up until it starts to boil. As soon as we start to have both liquid and gas in the same container, we've reached the boiling point of the solution, and that boiling point or boiling temperature will remain the same throughout the entire evaporation process until it becomes all gas, in which case we can heat it up again. And so that's what we actually indicate on our diagram. So we can see that this is an endothermic diagram because the energy is increasing over the course of the interaction. And the first thing that I do when I label a diagram is I notice if it's endothermic or exothermic. Endothermic is going to be a climbing diagram because heat is entering the system. And then the flat lines I'm going to label as my phase changes. And I know that because during a phase change, temperature remains the same. And then once I have my phase changes, I can go in and label solid, liquid, and gas. Solid is always going to be the lowest temperature rise. Liquid will be the middle between the 2 phase changes, and then gas will be the final rise. And so I've got solid, liquid, and gas, and I know that this is a phase change and this is a phase change. Well, I can label this first phase change between solid and liquid as both freezing and melting. Remember that freezing and melting are reciprocal activities, and it just depends on whether you're gaining energy or losing energy at that temperature. So we can say that this temperature over here would be the melting and freezing temperature of the substance if it was gaining energy at that temperature, it would be melting. If it was losing energy at that temperature, it would be freezing. In this case, we are gaining, so it would be melting. And so it's solid and it heats up, heats up, heats up, heats up, heats up until the first liquid particle shows up. At that point, the phase change begins, and so our temperature is going to flatline as we melt. And so we become less and less solid and more liquid until finally that last solid particle disappears and it's all liquid. Then our phase change is over and we're able to heat up again, and so our liquid is able to heat up until we get our first gas particle in the container. As soon as we get that first gas particle, then it is going to be boiling, because this is now its boiling temperature. This would be the boiling temperature. And it's going to continue to remain at that temperature as it becomes less and less liquid and more gas, until finally the last liquid particle disappears and it becomes all gas. And so that's an endothermic phase change. An exothermic phase change follows the same process, except for heat is going to be exiting the system. And so you're going to find your flat lines where temperature is remaining the same, and that's going to be your phase change. And then you're going to label your three phases. Solid will be at the bottom, liquid in the middle, gas at the top. And so then you can say, well, as a gas goes to a liquid in the forward motion of this, that would be condensation. But that temperature is also the boiling temperature, because those are reciprocal processes. And so it would be cooling down, cooling down, cooling down until the first liquid appeared, and then we would enter the phase change. The temperature would remain the same until it would converted completely into liquid and the last gas particle disappeared. As soon as the last gas particle disappeared and it was all liquid, it could cool down again. And so it would be in the liquid phase and cool down until we reached the point where the first solid crystal, ice crystal, would form, and then we enter our phase change, and so it's freezing in this case, and so it would be freezing, but remember this would be both the freezing and melting temperature, about 70 degrees. Would be both the freezing and melting temperature because they're reciprocal processes. Both solid and liquid would be in the container during this phase change. As soon as the last liquid particle solidified, we would be a solid and we could cool off again. And so that's what happens in a phase change diagram. So when you turn the pages to look at pages 36 and 37, you're just going to answer those questions. But before you do, what I want you to do for each of them is I want you to label the diagram. So you're going to label it, is it endothermic or exothermic? In this case, for diagram 37, it would be exothermic because heat was leaving. So you're going to label whether it's endothermic or exothermic. Then you're going to tell me, where are the phase changes? Well, we know the phase changes are going to be at the flat line, so this is going to be a phase change and this is going to be a phase change, because during a phase change, temperature remains the same. Then you're going to tell me, where is it solid, liquid, and gas? And remember, solids will always be the bottom rise, liquids the middle rise, gas the upper rise. Then you're going to tell me where the melting and freezing point is. Melting, freezing, and then also the boiling and condensing. You're going to tell me where those occur on the diagram. And then lastly, in step 5, you're going to tell me the process. So you're going to basically walk me through. It was gas and it cooled off until the first liquid particle, liquid droplet showed up, in which case the temperature remained the same as it became less and less gas and more liquid until, so this was our first liquid, until it became all liquid. At the point in which it was all liquid, it could cool off again until we start to get our first solid crystal. Once we reach our first solid crystal, the temperature is going to remain the same as it freezes until it is all solid. And then once it is all solid, we can cool off again. And so you would do that for both the diagram on 36 and 37, and then you're going to answer the questions as it relates, and then you can always come up and check my answer key if you need any help. All right, that is going to conclude phase changes and phase change diagrams. Thank you.